Hello there, my fly physics students. What I'm going to try to do is introduce some of the concepts of circular motion in this one. And circular motion has all of the same aspects of all the velocity and acceleration and force that we've been learning before, but it's in a circle. And so that might seem like no duh to you, but it it changes a few things in such a way that I think that it's not intuitive, or it doesn't always jump out at you as, oh yeah, this is what's happening. So I hope this video helps you to sort of understand the basics of how circular motion and what we would call linear motion are essentially the same thing. So let's say that that you are, oops, that's kind of a long arm. Let's say that you are doing this thing where, and you guys have probably all done this, where you got a string, with something attached to that string on the end, and you're whirring that around your head, right, in a circular motion. Well, it's definitely going. It has a velocity. But we talked about also how acceleration is a change in velocity, and that can include a change in direction. And so you'll notice that this thing is always changing direction, right? As it goes around the circle, it's always changing direction. So that means it always has an acceleration. And then if you would have realized on your finger, as you whir this around, you're always going to feel a pull on your finger, but that pull is going to continually sort of change sort of the position on your finger where it pulls. Like if it's over here, it's going to kind of pull on this side of your finger, and over here it's always going to pull on that side of the finger. But what it's going to be pulling towards relatively is, when it's over here, the pull is going to be a force that directs your object straight back to your finger. And so once your object is over here, you're going to feel a force on the other side of your finger that's going to indicate that that is pulling directly back towards your finger from this place, right? And so that force is always toward the center, or center seeking, or what we call centripetal acceleration. So here's a circle that I've drawn for you right here. And I'm going to draw a few radiuses in this circle. But if this is the center of the circle, and let's say that we're moving an object around here, right? So here's our object, and so each one of these radiuses is a position. So let's say I'm just arbitrarily going to draw a few. Let's say that I have this position, that position, and this position. Now we remember that velocity was a change in position over change in time. So if you're going along and right, so and you're moving along, and you got this position, and then that position, you would say, oh look, there was a change in velocity here, so there must have been an acceleration. Well, in circular motion, you can have a uniform velocity and then also have an acceleration at the same time. So let's call this radius 1, and let's call this radius 2, and let's call this radius 3. You can understand that these are radiuses of the circle. And so what we could say is, because velocity is a change in displacement, like this, a change in displacement over a change in time, there's a certain amount of time that's going to take for your object to whir from here to here to here. And so velocity in circular motion, right, equals a change in a radius over a change in time. Okay, so what does that mean? And how could we then draw the velocity here? So then if I was to say, what is the actual velocity? Like if I'm whirring this around the circle, right? If I was to let this object go, and you could try this. If you were to let this object go, it would probably, see if I can get my arrow tool. Let me use a different color right here. It would probably, here, let's do something more fun. It would probably go kind of like this, right off of that, right? And then down here, if you were to let this go right here, it would probably go something like that, right there. And then if you were to let this one go right here, it would probably go something like that. And if you don't believe that, all you got to do is take the string and whir it around your head and say, at this position, let it go, and it's going to continue in the velocity that it has at that position, which will be something like that. All right, so each one of these vectors right here is actually a velocity vector. So let's go ahead and go back to that color that we just had. So these are all velocity vectors. So I got, let's say I have velocity 1, velocity 2, and then down here I have velocity 3. Now there's a particular angle right here, right, and there's a particular angle right here. Now let's just say, for the sake of understanding that these are the same angles. So that means that if this angle and this angle is going to correlate, because these vectors come from the same thing, is going to correlate to these vectors right here. So if I was to take these velocity vectors, say, and put them together, so I'm going to take this velocity vector and this velocity vector, let's see, and I'm going to take this one and I'm going to try to draw it, the same. So let's say I've got that one right there, so that's my V1, and let's say I've got my my V2, right? So there's my V2 right there. Now, if I was to say, okay, well, what about this triangle right here, and this angle right here? Well, because these velocity vectors come off of these radiuses from these change in positions, they're similar triangles, right? And so this right here, this if you were to take this vector right here and sort of measure that out, that would actually be the change in velocity. So what we're trying to get at is an acceleration, right? So we know that a change in velocity over a change in time is an acceleration, okay? So if we were, let's go ahead and grab a different color. If we were to take, and so we understand that the change in velocity is going to be the resultant of these two velocity vectors, and that they're similar angles and similar, so that makes them similar triangles, because this is the same angle that has been made here. So that change in velocity is actually, if you look at it right here, it forms a, if you take this right here, it's going to form a right angle with this bottom part of that. Okay, so I'm going to draw that right there. Actually, let me go ahead and draw that as an angle, or as a, let's see, I can get a different color here. I'm going to go red. Okay, so that right there, if I was to draw that, and you're going to see that it does this, right? If I was to take that, because it's at a right angle from those velocity vectors, it does that. And so what are those? Those are change in velocities, right? Those are change in velocities. And what do you notice about all the change in velocities? Well, all the change in velocities, which we know, right? Change in velocity over change in time equals acceleration, right? So you notice that all of my acceleration vectors is toward the center. And so that sort of makes sense if you remember the thing whirring around your head, and that you're having to continually accelerate this thing that you're whirring around your head back toward your finger. If you accelerate it back towards your finger, then what's going to happen is it's going to continue to move around the circle. And the minute that you stop accelerating it back towards your finger, it's going to fly off in whatever direction that it was going. Right? And it's going to just continue in that direction. So the acceleration vectors are center-seeking, and in center-seeking, that's why we call it centripetal acceleration. So centripetal means center-seeking. So this is centripetal acceleration. All right, well, let me sort of explain a couple of things, because let's go back to my radiuses. So as I change around the circle, my radius changes from here to here to here to here. and each one of those radiuses at each particular thing has a particular velocity, and those velocities change as my radius changes. And like I showed you, I took those velocity vectors out here, put them together, and made the change in velocity right here, and then I took and I put that, I should have probably put this one in red and actually put it in this direction. And then what I did is I just sort of transplanted that over here to show you the acceleration vector. Well, because the same angle exists between the radii of the velocities as exists between the radii of the radiuses, so the ratio of their lengths are the same. And so what I'm going to do is at this point I'm going to go ahead and just stop this video, and then in the next video what I'm going to do is I'm going to show you how do we solve for an acceleration moving around a circle. But I hope this helps to sort of make the idea more intuitive as to where in a circular motion are your velocities, where are your positions. So your positions are your change in your radius. Your velocities are whatever the velocity is at that particular position. So as this is moving around the circle, right here, my particular object is moving in this actual straight line. But I continue to pull on it, right? I continue to pull on it, and my pull is toward the center, causing an acceleration toward the center. And so Newton said that, force equals mass times acceleration, right? So the same is true here. You have what we call centripetal force, which is a center-seeking force. So centripetal force means that the force is always toward the center. And so for a circular motion to work, you have to have a continual force pushing it toward the center. And of course, the acceleration is in the direction of the net force. And so we could say that, and we could actually, for centripetal acceleration, we'd have to say that the force net is going to equal the mass of the object times the acceleration of centripetal. Now, acceleration of centripetal isn't as easy as linear acceleration to solve for. It still is just a change in velocity over a change in time. Like I said, these are my changes in velocity, so all my changes in velocity I could draw resultant vectors. That would give me my accelerations. Notice that all my accelerations, if I put them back in the circle, go toward the center. But to solve for this, it's a little bit different because time is going to be something that actually is a factor of the circle itself, and you're going to have pi, you're going to have radians, you're going to have all sorts of different things in there to solve for it. So in the next video, what I'm going to do is I'm going to show you how do we take what we learned in this video, and then how do we get the equations for acceleration out of that. All right, so stay tuned for the next video. We're going to derive that equation.